produce the halo. You don't get you can't see the halos unless there's been millions of these alpha particles produced. And it has to happen in a very short period of time because the polonium only lasts on the order of months at most. It's a very rapid decaying material. Some of them only last a few seconds and minutes, some of the different isotopes, but the longest lasting isotope lasts on the order of months. So these radiohalos, these polonium radiohalos that are produced, there has to be millions of alpha particles. They have to be produced in a matter of a few months, and it has to be in solid rock. If this decays in magma, it doesn't produce the damage. And in fact, if it's produced in rock that's hotter than about 150 degrees centigrade, the halos go away. The damage heals itself. It's called annealing. So you have to have solid rock. It has to be colder than 150 degrees centigrade, and it has to happen in just a matter of a few months. So that means these big plutons of granite that we find like in the Sierra Nevada, up in Yosemite and various places, that rock had to have cooled from a magma to solid rock cooler than 150 degrees centigrade in a matter of weeks or months at most in order for these halos to form. And if you look at the decay rate at which polonium decays today, you couldn't get millions of these alpha particles produced to produce the halo in a matter of months. It has to be millions or billions of years. So again, it would appear that you got billions of years, but it had to have happened fast. So it had to be a catastrophic increase in the decay rate. Again, evidence for accelerated decay. Okay, now we've plotted some very interesting features here. This is radiohalo number per slide, and we've actually processed over 10,000 slides in this sample. And they're plotted in numbers per slide as a function of conventional age, based upon the rocks that they were collected from and the conventional age that's assigned to them. And you'll notice that most of the polonium radiohalos occurred in this region here between about 65 million and 500 million years old. We believe those are the flood rocks. Now, it makes sense if you had a catastrophic flood process where all this water was flowing through the rocks, displacing the polonium halos, that it would occur at the same time. So we have very strong evidence that this accelerated decay was associated with the flood. It was not caused by the flood, but it was associated or at the same time as the flood. And it didn't happen in older rocks, according to conventional ages, or in younger rocks. It doesn't go on today. Again, you can't observe that actually going on today. It doesn't happen today. And it didn't happen early in Earth history. It only happened, we believe, at very specific times. Okay, another one, I'm going to have to go fairly quickly here to get through all this. Dr. Austin, for a number of years, even before the R.A.T.E project started, was looking at the disparity between ages calculated on rock samples from different locations and for different type tests in the same location. One of the favorite places that he's collected rocks, and we've done many more, is in Grand Canyon. I'm sorry, let me back up here. In Grand Canyon, you have all the various layers that you're probably familiar with, but down in the bottom of Grand Canyon, there are layers that are interspersed with magma that's come through cracks, and it produces these layers of magma, hot magma, that is igneous type rock that is suitable for age dating. Sedimentary rock is very difficult to age date because it's made up of other rocks that were broken up and settled in water and form new kind of rock. But if you have igneous rock, you can date it directly, and you notice it will intersect down in the Grand Canyon at various places. And if you look at the top view, along the Colorado River, there's outcrops of cardenous basalt and various sills and dikes that are made up of this igneous material. And one of the best ones that we worked at is the Bass Rapids. This is one that Dr. Austin and the R.A.T.E group looked at very carefully. Now, this doesn't happen to be at that location, and the samples we collected here were tough instead of igneous rock, but it gives you some idea if you've never been down in Grand Canyon. We take tours there about every 2 or 3 years, and we'd love to have you. The next one's going next spring. Here's a favorite place where samples are collected of tuff, and even the various other government agencies collect in the same place. Okay, now here's a rather complex diagram, and I don't have a lot of time to spend on it, but it's a composite of both Dr. Austin's and Dr. Snelling's data for various types of decay processes. We have in the vertical axis here what's called an isochron age. Now, this is a particular method for estimating how old a rock is using isochron techniques, which is a bit involved. You'll have to buy the technical book when it comes out this fall to get the description of that. And on the horizontal axis is the atomic mass of the material. For example, potassium-40 has an atomic mass or atomic weight of 40. Rubidium has an atomic weight of 87. Samarium and uranium-238, which is way out here. We can then, from each of those techniques, estimate what the age of a particular rock is. Now, these are samples all from the Bass Rapid Sill. The Bass Rapid Sill down the bottom of the canyon. It's the same formation, and the yellow one in particular. You'll notice that there are different dates for the isotope that you use, and you'll notice that it tends to go up based upon the atomic weight. And for some of the other type of rocks, which are granite-like, the green ones, for example, they go up as you go up in atomic weight. There seems to be some interesting trends here based upon atomic weight, which we don't fully understand yet, but the distinction is these error bars aren't even crossing each other. In other words, even for the same type of sampling, we get different estimates of age outside the error bars for the different types of material. Now, the ages are on the order of 1 billion years or so, which we wouldn't agree with, but the fact is that they don't even agree with each other. They're all out of agreement, or what's called discordant. So for the same rock sample, you get different ages based upon the different type of isotopes testing that you're doing. That's quick. I know it's quick, but there's a lot of more information in the books that we're producing. Okay, here's an exciting one. Carbon-14, Dr. John Baumgartner, trying to find carbon-14 in bones and coal. It turns out just about 15 or 20 years ago, a new technique called atomic mass spectroscopy was able to measure the concentration of carbon-14 at extremely small levels, much lower than anybody's ever been able to before. And for about 15 years, there was some 70 reports in radiocarbon, the standard literature for this field, reporting on this, but we didn't find out about it until about 3 or 4 years ago that this was being done. And the reason there were so many reports was they kept finding carbon-14, and there was no way that they were going to admit that the carbon-14 was real. It must be due to contamination in either collection or in the way in which the samples were handled in the laboratory. So they kept reporting this, trying to get rid of all this problem. They never could. They finally come to the conclusion that the technique is valid, that they're actually finding carbon-14. But nobody has had the guts in the conventional community to say, we got a problem. In coal, there should be no carbon-14 if it has a half-life of 5,700 years, and the coal is supposedly 100 million years old. There should be no carbon-14 left, but it's there. It's measurable quantities. Well, Dr. Baumgartner confirmed this by looking, well, let's talk about carbon-14 briefly here. This is in the atmosphere. Carbon-14 is actually produced by cosmic radiation. You got both carbon-12 and carbon-14 in the atmosphere, but carbon-14 is produced as cosmic radiation strikes nitrogen-14 and breaks it apart. This carbon-14 is incorporated into living organisms like plants and animals, just like the carbon-12 is. And the ratio between the two is the same basically as it is in the atmosphere, as it's incorporated by plants, and then animals eat the plants and so on. And then when the animal dies, this carbon-14 continues to decay, so you can actually estimate how long ago it's been when the animal died, as this carbon-14 turns back to nitrogen-14. So you can use that as a dating technique. Okay, now what happened during the flood? If this material in the atmosphere was built into the trees, and suddenly the trees were buried in the flood, here's the flood coming along, burying all these trees, compressing it under the sediment layers and forming coal, then the coal is continuing to decay, and the carbon-14 is turning back into nitrogen-14. And you can date the coal. If there's carbon-14 there, it tells you that the coal is young. And that's, in fact, what we find.